All right. So I sent you an email earlier this morning with a tip on homework 9, which is due on Wednesday. And what I wanted to let you know about that problem is that there's another way to solve for flow per unit width. And you might have already derived this yourself, but remember, flow per unit width, lowercase q, means the flow width, large Q, divided by the channel width B. And this is something that we do for rectangular channels. So now, remember, Q is the same thing as velocity times area. And for a rectangular channel, area is the bottom width B multiplied by the depth Y. And so if you do that cancellation of like terms, then what you'll find is the flow per unit width, lowercase q, is not only q divided by b, the bottom width of a rectangular channel, but it's also the flow velocity multiplied by the depth of the channel. So in that problem, 1222, you are given the flow depth, and you're given the velocity of the flow. So you can use that to find flow per unit width. So you can find flow per unit width, lowercase q, and use that to determine the critical depth, because you know the critical depth can be calculated as flow per unit width squared divided by g to the 1/3 power if it's a rectangular channel. And so then one of the ways that you can tell if the flow is supercritical or subcritical is Froude number. But then the other way is to compare the flow depth to the critical depth. So what you'll find in that problem, 1222, is you can find y sub c and compare it to the given depth that they tell you. And then whether it's supercritical or subcritical is going to tell you which root of the cubic equation to select as the solution that we're looking for. So just a couple of hints there, and I'm actually going to give you a couple of hints on another problem on that assignment in just a moment. The next reminder about our design project. The pipe network sizing initial submission is due on Friday, April 2nd. Now I'm going to continue working on the assessment of your demand estimation, and I'll be giving you that feedback this week. But you know, if you get your feedback too late to incorporate it into this draft submission, that's fine. This draft submission is really to lay out where the pipes are going to be and find out the required size of the pipe based on your initial estimates of the flow demand. So it's in the very end that we can make all of the updates and all the corrections based on the feedback that I give you. But what you need to submit, as I mentioned on Friday, for phase 2 is 2 maps. And I don't mind if you create those maps from within EPANet, or if you sketch it by hand on top of the printed map that I've provided, as long as you, or you can do it some other way, like you could do it with AutoCAD, or you could do it with PowerPoint. But the annotation is the important thing, so that I can see when you turn in the maps what's the diameter of the pipe, what's the length of the pipe, what's the elevation of the junction, how much flow is coming out of the junction, what's the pressure at each junction. With the annotations, then that'll help me to know how close to the edge you're getting on this design. And you should be close to the edge. That's efficiency, is remember the idea that you're just barely making the system work. That's the optimal design, as long as the criteria that you're setting are an acceptable criteria. Then at your design flow rate, you don't want to have 500 kilopascals everywhere in the network. You want to have as close to 240, which is the lower limit, as is possible. Okay, so that's due on Friday, and then our next exam is about a week and a half from today. It's going to be on Wednesday, the 7th of April from 12:30 to 2:30, and we'll talk more about that. But long story short is the format is going to be similar to the format on the first exam, where it'll be available on Blackboard, you'll submit it on Blackboard, and you'll have 2 hours to take the test. Any announcement related questions before we move on? Okay, we'll talk about chokes and contractions today, and this is just an application of specific energy. But I mentioned I had one more hint on the homework that I wanted to give you, and so here's this. In the homework problem 25, homework 1225, I think it's the second one of the 3 that I assigned, is a channel that's expanding from 5 foot in width to 10 foot in width. And they're asking what's going to be the new depth of flow downstream. This is just another equation where you're solving a cubic equation and you're going to find the root that goes along with whether you had supercritical or subcritical at the upstream depth. So let me show you a couple of specific suggestions. So you know the flow widths at the upstream and downstream location, and they tell you that at the upstream location, before the channel got wider, we know that the depth was 4 feet and the flow velocity was 4 feet per second. So if you know B and Y, that's the cross-sectional area, right? For a rectangular channel, area is the width times the depth. So it's 20 square feet, right? And if you multiply that by V, then it gives you Q. So Q equals VA. So we have everything we need to know what's the flow rate Q. And the flow rate in the narrow section is the same as the flow rate Q in the wide section. But what changes is the flow per unit width. So remember, lowercase q means it's the flow divided by the width of the channel. And they also are mentioning an expansion factor. And this is kind of like a, you can think of it as a local loss. It's an expression that describes what happens in terms of specific energy when a channel either gets narrower or wider. And here they tell us it's 0.5. So let me show you what to make of that. Now here's some of these equations that we've already talked about. Q equals VA. So you can find the flow rate in the narrow channel. And because of continuity, flow in equals flow out. So you'll notice here, although I have lowercase q1 and lowercase q2, the Q is the same. It's not like there's capital Q1 and capital Q2 because they don't change. The width changes, and so therefore the flow per unit width is different at 1 and 2. But big Q is the same upstream and downstream. So any questions so far with the setup on this problem? Okay, you'll notice I also gave you the formula here for the critical depth based on the flow per unit width. That's good to have, and you can use it to assess whether the flow conditions are supercritical or subcritical. You could also use the Froude number, of course, at 1. They want you to know the new downstream flow depth, and so the way that you can do that is with this formula. This is just the specific energy formula. It's saying that the specific energy at 1 is equal to the specific energy at 2 plus the losses. And so here, this plus C times the velocity head is the amount of energy that's lost in the channel because of the expansion. So you're losing 50% of the velocity head with the expansion. So here are the steps that I'm suggesting in the bullet points is that with this equation, you're going to have a cubic equation. And we can write velocity head in terms of V1. I think that you've seen me in previous classes tell you the velocity head can be in terms of Q1. So here, see the velocity head Q squared divided by 2GA squared. So that's another way to write velocity head. And now here's another. What I'm saying is that we can also write the velocity head in terms of flow per unit width, lowercase q. So here's the velocity head. And the reason why this is advantageous for us is that it allows us to solve for the unknown depth, y2. Okay, so the only unknown in this equation is y2. So then you'll multiply each term by y2 squared, and that gives you the cubic equation. You solve for the roots, and then whether to choose the supercritical root or the subcritical root depends on whether at location 1 upstream you had supercritical or subcritical conditions. So it's essentially the same process as everything we've been doing with specific energy. Just the new rub is that we add another term at the end for the expansion coefficient. Any questions before we move on? I hope this hint kind of streamlines how long it takes you to solve this problem. This one's due on Wednesday. So if you do have any questions pop up, feel free to reach out. All right. Now, let's review what we talked about on Friday's class. In Friday's class, we talked about what happens when there is a change in the elevation of the bottom of the channel. Because specific energy is how much energy is there above the channel bottom. And so if we're saying our datum is the bottom of the channel and then the channel itself drops down, then that's going to affect the specific energy. Here on the left, the specific energy is going to be greater at 2 because of the delta Z. Whereas if it's a step up, then there's less specific energy at 2 because of the step. So this is what we've seen in previous classes, is that E2 is E1 plus the delta Z if it's a step down, or if it's a step up, it's E1 minus the delta Z. And E has two components. It's the depth of the water, Y, and then it's also the velocity head. And we can write the velocity head a lot of different ways. We can write the velocity head as, I guess, I'll show you the next one. We can write the velocity head in terms of v2 squared divided by 2g. So like that's the velocity head, or q squared divided by 2g a squared. That's another way to write the velocity head. Or here we saw that you can write the velocity head in terms of flow per unit width squared divided by 2gy squared. So any one of those is going to give you the velocity head, but in this equation I just wanted to write them either way just to illustrate that velocity head can be in terms of flow, and the convenience of that is that we often don't know what the new depth is going to be. So y2 is an unknown, and because the flow velocity depends on y2, then it's just easier for us to have that y2 unknown as part of the area. So that's just a review of what we talked about last week. Bed step down, bed step up. But there's a limit to how big this step can be. Not the step down. There's no limit to that because the flow is gaining energy. But the flow is losing energy if we have a bed stepping up. And so there's a maximum delta Z that can be tolerated. And the flow depth changes whether there's a step down or a step up. The new downstream depth y2 is going to adjust in reaction to that. So we can use the specific energy diagram to predict whether it's going to step down or step up. Let's think about for a really small step up. If this is subcritical flow, and if we have a specific energy diagram, and we'll look at one in just a moment, what that means is that you had some original depth and the flow depth y2 decreases. If you have a bigger delta Z, then that decreases the flow depth downstream even more. And now there's going to be a limitation. There is some step height that is the biggest step height that can be tolerated without disturbing the flow, without causing any choking upstream or pooling of the flow upstream. There's this maximum step, and what it corresponds to is it's the step that corresponds to a flow depth of the critical depth. And I told you this, this idea that the minimum specific energy is associated with the energy where the critical depth, you've got critical conditions, that's the minimum specific energy that can convey a certain amount of flow. It's the most efficient depth, the critical depth. You can get the most flow through with the least amount of specific energy when conditions are critical. But if you have the step even higher, so this delta z sub d, this is just like A, B, C, D. This is just like different situations. Situation A, situation B, situation C. Here in situation D, in the fourth option, they tried to make it even taller. And what happened is now that step up is so big that the water has to get additional energy to flow over the obstruction. So it pools upstream. There's choking, as they say. So there was this original depth, y1, but then because the step up is so tall, the flow has to get even deeper. And so y prime 1 is referring to the new depth that will set up after water comes into equilibrium again. Now here in case C, you may remember that we said 2/3 of the specific energy exists as depth when it's critical flow, and 1/3 of the specific energy exists as velocity head when conditions are critical. So that's just when you've got critical conditions that there's the 1/3, 2/3 distribution between flow depth and velocity head. So here's the specific energy diagram. And so our original flow depth, y1, encountered some step. And so y1 is just the upstream depth. And so if we have a step that is as high as delta ZA, then that decreases our specific energy. And so here now is the amount of specific energy that remains. And so that made the depth get lower because of the step. And if we had delta ZB, then the step up is even bigger, so that's extracting more specific energy, and so there's less available for this now downstream depth y2. And the critical step height, the delta ZC, is the step height that's associated with the critical depth and the minimum amount of specific energy for a certain flow rate before pooling occurs. And if we go even beyond that, then we're no longer on the specific energy diagram. So if you have the delta ZD, the step is so large that there is no depth that is associated with that. We're not on the curve anymore. So what would happen is that the water has to continue pooling upstream. So the conclusion is that a step larger than the critical step will mean that there isn't enough specific energy, and so the flow has to back up. And there's an accumulation of energy. That's what pooling is. You can think about it in terms of flow rate, Q in and Q out. So Q in to a control volume is going to be larger than Q out if you have this big delta Z, because the water can't flow over the obstruction, and so there's going to be water coming in but not water coming out because there is not enough energy to get over the obstacle. And so what happens is that water is getting deeper upstream until it accumulates enough energy. So E prime 1 is the amount of specific energy after pooling occurs upstream. And so then that's the new amount of specific energy that will have enough energy available to get over this obstruction. So E1 was how much specific energy there was before the obstruction was encountered. But then E prime 1 is after pooling occurs. And so Y1, by the same token, is just the original upstream flow depth, and then Y prime 1 is how deep it gets after the flow is backing up. So you have to ask yourself, why is the water getting deeper? Because it has no choice. Flow keeps coming towards this obstruction, and so there's going to pool and accumulate water, and then it will finally stop accumulating, and it'll come back into equilibrium when there's enough energy at 1 so that water can flow at the critical depth over the obstruction. So Y sub C, you'll notice in this diagram, this is kind of showing what happens after pooling. It's going to flow at the most efficient depth possible, which is the critical depth. The pooling will occur upstream until there's just barely enough energy to get over the obstruction. And so the minimum amount of specific energy that's required to get over the obstruction is associated with critical flow depth, YC. Okay, so just that second look at the specific energy diagram, we need to have a new specific energy diagram. That a new curve is going to be required so that there's enough energy to get over this obstruction delta ZD. Okay, so these are abstract ideas. Let's make it a little bit more concrete and a little bit more real by doing a calculation where we say that we have a rectangular channel. You can see here a cross-sectional view. The depth is 0.9 meters at this upstream location. Location 1 is upstream, and we know the flow rate is 4.25 cubic meters per second. And the depth there originally 0.9, and the width of the channel is 2.5. So since you're given the flow rate Q, and you know the width of the channel, then you can calculate the flow per unit width. And if you know the flow per unit width, then you're going to be able to diagnose the flow regime, or you could use the Froude number. But we're going to want to know whether conditions are supercritical or subcritical upstream, because it often comes into play when we find routes downstream. Now at location 2, we're going to find out the new flow depth when there's this step up, so a delta Z of 0.05 meters, and then we're going to solve for how big could the obstruction be before choking. So that's kind of the maximum allowable delta Z. And what I say is, just before choking, the water depth at the constriction is going to be the critical depth. So we're going to, in the second part of the problem, in part B, we will say, let's make it so that Y sub C is the downstream depth, and now the unknown becomes delta Z. So in the first part of it, the unknown, delta Z is given, and the unknown is Y2. But then in part B, we know the depth. We'll have it be the critical depth, and we'll solve for the delta Z max. Okay, so I tell you the steps here. Find V1, find the Froude number at 1, find the amount of specific energy at 1, and then find Y2. And it's the form of the equation that we use here is the same as all of the other ones that we've done so far. Let's say, for instance, this one. Let's see. We've got a step up. Yeah, this would be a good one. Let me copy this over for the problem, because it's a step up. So think of this second term as just the velocity head. So you can substitute either the flow rate and the cross-sectional area in, or it can be v squared divided by 2g. All right, so let me put you into the breakout rooms here. We're going to try and find out these two things. What will be the new flow depth, Y2, when you've got 0.05, and then the second part is how high can the step get before there's choking. Okay, welcome back. Now, let's see if we can find, first of all, what would be the flow depth for a given obstruction, and then part B, how high can that obstruction go and just barely prevent the choking. Okay, so here's a view of both cross sections. The second cross section is the excuse me, same width, it's just we've got a step in the way. So at 1 we can calculate the velocity and the flow per unit width. And what we know is that the energy at 1 minus delta Z is how much specific energy there is at 2. Because the delta Z stepping up over that obstruction is going to reduce how much specific energy there is at location 2. So E1 includes both the depth and the velocity head. Then we subtract out the delta Z, and then what's left is going to be the energy at 2. And so those things are, here's our initial flow depth of 0.9 meters, the initial specific energy, the initial velocity head at location 1, and then the step up. So all of that, if we do the calculations, means that at location 2, there's going to be 1.0319 meters of energy available. And that's going to be distributed between the depth and the velocity head, but we don't know exactly how much is going to go into each, and so that's why it's convenient to express the velocity head in terms of the flow rate Q. Okay, so the channel is still 2.5 meters width, and so the area, you can see down here in the denominator, the area is 2.5 times y2. So because it's rectangular, it's the width of the channel times the depth. And then we also have the y2 as the depth itself. So the beginnings of a cubic equation, then we multiply each term by y2 squared. And now we have that cubic equation. And solving for the roots means that we have here is a supercritical root and there is a subcritical root. And we don't specifically know which one to choose because in theory it could be supercritical or subcritical, although you know subcritical is more common. Even in relatively steep areas like here in West Virginia, most of the streams that we encounter will be flowing subcritical. But you always have to check because it's the exception that can be deadly or expensive. So here we had a Froude number less than 1, and so that means we choose this deeper downstream depth. And so when we have that step up of 0.05, then that's going to reduce the flow depth to 0.804 meters. So the original depth was 0.9 meters, and encountering the obstruction means that the water gets shallower to jump over. And then remember, you know, from kind of a graphical reason, why does it become shallower? Think about the specific energy diagram. What we're doing is we're losing specific energy. We were at some initial depth here, and the next crossover point in the subcritical range of the specific energy diagram would be a reduced depth. So it's like we're going from y1 down to y2 because of that step. So any questions so far on this part of it? Okay, part B is asking what if we want to go as high as possible? What's the biggest step that can occur to just prevent choking? So we're going to say, let's have it be critical flow depth at 2, and then we'll solve for the unknown delta Z. All right, so if we want the maximum delta Z, then that means y2 is going to be the critical depth. And so we can solve for that since it's a rectangular channel using flow per unit width squared divided by g to the 1/3 power. 0.665 is the critical depth here. And if that's the depth, then we can directly solve for the velocity, because the velocity is simply going to be q divided by a. So it's going to be flowing at a speed of 2.555 meters per second. And so the energy equation is specific energy at 1 minus delta Z equals, which means if we're minusing the delta Z on the left-hand side of the equation, then we could add it to the right-hand side of the equation, which is, you know, as how I've written it here. So there's the energy at 1, the energy at 2, and the only unknown there is the delta Z max. And so the highest that step can go is 0.084 meters. And if the flow goes any deeper than that, then pooling has to occur upstream. Okay. So are there any questions before we move on from this example, or how you find the new depth? So if you get the step too deep, then it chokes the flow. Choked flow just means that the maximum constriction has been exceeded, and the maximum constriction will cause the critical flow over the obstruction. And if we go any further, then the upstream water elevation has to get higher. So the increased depth is what allows us to accumulate energy until there's enough to get over the obstruction. So let's just go through the illustration here. Let's say, what if we had water going through a channel at a depth of 10 feet? It's just moving along, steady, uniform flow. What if the depth was 10 feet? And then somebody dropped an obstruction in the way. There was an obstruction, a really famous obstruction was in the news the last few days, right? A ship in the Suez Canal. So channel obstructions don't usually make the news quite so prominently as that. But what if this obstruction in our example, instead of blocking the channel sideways, what if it was blocking the channel vertically? So that's what's happening here, is we put in some obstruction that is itself 10 feet tall. So we know just instinctively, if the water was 10 feet and now you put in an obstruction that's 10 feet, it can't continue flowing under normal conditions. You know, 10 feet isn't going to be enough depth upstream to get over that obstacle. So the water has to get deeper. And the question is, how much deeper does it need to get to go over that obstruction? Well, what we know is that the water will pool upstream until there's just barely enough energy to get over the obstruction. So there's enough energy to get over that obstruction once you achieve critical flow over the obstruction. So when we're back into equilibrium again, then we'll have critical depth over the obstruction, and then we'll have some unknown y prime 1. The prime just means it's pooled upstream until it gets back into enough energy to get over the obstruction. So it's a new equilibrium. So our process to find that upstream depth is you would find out how much energy is required. So the E required would be the obstruction height, delta Z. So here it's 10 feet is our obstruction height. And then the minimum specific energy is going to be the flow depth and also the velocity head associated with that flow depth. And if it's the critical flow, remember E minimum is 3/2 times the critical flow. Because, well, that's if it's a rectangular channel. And just for simplicity, I like to make as many of these rectangular channel as possible, because it gets really tricky if it's trapezoidal and then you're doing specific energy calculations on top of that. Because then the width of the channel varies as a function of depth as well. I mean, it's doable, but it makes things more complex. All right, so we find out how much energy is required. So it's the delta Z, and then you could find the flow per unit width of the channel, and with that find the critical depth, and with the critical depth find the minimum specific energy. We have an example flow rate here. Like if it's 500 CFS and the channel width is 10 feet and the original depth was 10 feet and then this obstacle gets dropped in, we would want to know how much is it going to pool upstream. So I'm going to just show you the calculations. We've only got 6 minutes of class remaining, so there isn't enough time for me to turn you loose on this yourself. I'll just have to show you the calculations. But what we'll do first is we'll determine whether there is going to be choking. So we'll compare the required energy to how much available energy there is upstream initially. We can tell just from inspection that 10 feet is too high of an obstruction. But we'll go through the paces, the more generally applicable paces here, because you know, what if it had been 8 feet? You know, maybe the flow can get over an 8-foot obstruction. So the way that you know is you compare the required energy to how much is available. And then if choking will occur, then you'll find out the new depth that corresponds to the required energy by adding in the delta Z. Okay, so let me show you these calculations. So this is 500 CFS. The channel is 10 meters wide. And then we have an initial flow depth of 10 feet. And we want to find out what will be the Y prime one. That means the new flow depth after the pooling occurs. Okay, now I've calculated the critical depth for a flow per unit width of 50 feet squared per second, because it's 500 CFS divided by a 10-foot wide channel. So then that makes lowercase q is 50 squared divided by g to the 1/3 power. So the critical depth is 4.265 feet. And then minimum specific energy, there has to be at least 6.398 feet of energy to get over the obstruction, because the minimum, like best case scenario, most efficient, is it's flowing over here at the critical depth. And when it's critical depth, we need to have enough energy for it to be the y of the critical depth plus the velocity head on top of that. And the velocity head will be 1/3 of the total specific energy. Okay, so there has to be 6.4 approximately feet of energy. And so the required energy in total would be the obstruction and the specific energy. So there has to be 16 feet of energy available at 1 for the water to flow over the obstruction without any pooling. And I think what we're going to find is that there is not that much initial energy available. Boy, I wish this is a little bit neater. I apologize that my handwriting is a bit sloppy. So how much energy is available initially? So it's going to be the flow depth of 10 feet and then the velocity head. And the initial velocity head I've expressed in terms of the flow per unit width. Just with some practice of that, what you'll find is that there's 0.388 feet of head at this particular flow depth configuration. So there's less available energy than how much is required. So the 16.39 says you have to have 16.39 feet of energy to get over the obstruction, but initially we only have 10 feet, 10.38. So the water must pool upstream. So the conclusion, since the required energy is more than what's available, then choking will flow. Choking will occur. This sill, that's just another name for the obstruction, a sill. The sill is choking the flow. So then the new upstream depth, we're going to say that the required energy, which we know it has to be 16.39 feet of energy to get over the obstruction, that's going to be in the new upstream depth and then the velocity head as well. And now you can see why it's convenient to express the velocity head in terms of flow per unit width, because we still know the flow per unit width. That's still 50 feet squared per second, but we don't know the new upstream depth y prime 1. So we see the beginnings of another cubic equation, and of the two roots, obviously the smaller of the two roots, a depth of 1.6 feet would not be adequate to overcome that obstacle that's 10 feet tall. So the water has to pool until it gets to 16.25 feet of depth. And so once it's at that depth, then there's going to be enough energy to overcome the obstruction. Okay, so that's all the time we have for today. What we will do is practice these same notions on Wednesday's class with this illustration. We'll do this example on Wednesday. But remember, you have a homework assignment that's due on Wednesday. And I've given you hints via email and then also here on this slide for the first of those two problems. three. There's three problems. So here's the first problem. The second problem was this one that I gave you some hints on. The third one, I guess you're on your own. But if you have questions or you want to check your answers, definitely get in touch and I'd be happy to hear from you. And that's it from today. Oh, sorry, I just noticed a question from Logan here. After the obstruction would go back to 10 feet. It depends on the channel. Like if it's just the same channel with the same roughness, then yeah, it would flow over kind of like a weir and it would go back to its normal depth. So yes, it would. That's it, everybody. Take care. Hope you have a good one.